Welcome to Section 6, Lesson 8. In the previous 7 lessons, we built every solving technique for systems of equations, including substitution, elimination, special cases, 3, variable extension, and word problem applications. Today, we extend the system solving toolkit from equations to inequalities. A system of inequalities consists of 2 or more linear inequalities that must hold simultaneously, and the solution is no longer a single point or a line, but an entire 2-dimensional region of the coordinate plane, the intersection of the half planes corresponding to each inequality. Today, we lock in the half-plane intersection technique, the corner point identification, and the application of these systems to feasible regions for linear programming. First idea on the board. A system of linear inequalities consists of 2 or more linear inequalities, like a x plus by less than c or x plus by greater than or equal to c, that must all hold simultaneously. Each inequality alone describes a half-plane on the coordinate grid, the same region we covered in Section 4, Lesson 8. The solution to the system of inequalities is the intersection of all these half-planes, the set of points that satisfies every inequality at once. The intersection is typically a polygonal region with straight line boundaries, sometimes bounded with finite area, and sometimes unbounded, extending to infinity in some direction. To solve a system of inequalities graphically, graph each inequality on the same coordinate plane using the half-plane procedure from Section 4. Identify the boundary line type for each, solid or dashed, based on whether the inequality is non-strict or strict. Shade the half-plane that satisfies each inequality. The final solution region is the area where all the shadings overlap, often shown by darker shading or by explicit boundary outlining. This is the feasible region of the system. Third idea. The corner points of the feasible region, also called vertices, are the points where 2 of the boundary lines intersect within the feasible region. Each corner is the simultaneous solution of the 2 inequality boundaries treated as equations, found by solving the corresponding 2-equation system using substitution or elimination. The corners are foundational because in linear programming, the optimum of any linear objective function over the feasible region always occurs at one of the corners. Today, we find the feasible region and its corners for 2 example systems. A system of linear inequalities is 2 or more inequalities that must hold simultaneously. Each inequality describes a half-plane on the coordinate plane, and the solution to the system is the intersection of all these half-planes, the region where every inequality is satisfied at the same time. Here is the graphing procedure. Step 1 is graph each inequality individually using the half-plane method from Section 4, Lesson 8. For each inequality, draw the boundary line as solid or dashed depending on the strictness, then shade the half-plane that satisfies the inequality using the test point method. Step 2 is identify the intersection of all the shadings. The feasible region is the area covered by every inequality's shading simultaneously, which means it must be inside every individual half-plane. Visually, the feasible region is the darkest shaded portion of the plane after layering all the half-planes. Geometrically, the feasible region is a polygon when the boundaries are line segments with straight line sides corresponding to the boundary lines of the inequalities. Step 3 is find the corner points or vertices of the feasible region. Each corner is the intersection of 2 boundary lines treated as equations solved using the system solving methods from earlier in this section. Corners are foundational locations in the feasible region because linear programming optimization always finds its optimum at a corner. Step 4 is classify the region as bounded or unbounded. A bounded feasible region has finite area with all corners enclosed inside a closed polygon. An unbounded feasible region extends to infinity in some direction, with at least one boundary running outward without closure. The classification matters for optimization. Linear programming problems with bounded feasible regions have guaranteed optimal solutions at corners, while unbounded regions may produce optimization problems with no finite optimum. Here is the first worked example. Graph the system of two inequalities, x plus y less than or equal to 4 and x minus y less than or equal to 2. Identify the feasible region and any corner points where the two boundary lines meet. Step 1. Graph the first inequality x plus y less than or equal to 4. Boundary line is x plus y equals 4, drawn solid because the inequality is non-strict. The line passes through 4, 0 and 0, 4. Test point 0, 0 plus 0 equals 0 less than or equal to 4. True. Shade the half plane containing the origin, which is below and left of the line. Step 2. Graph the second inequality x minus y less than or equal to 2. Boundary line is x minus y equals 2, drawn solid. The line passes through 2, 0 and 0, negative 2. Test point 0, 0 minus 0 equals 0, less than or equal to 2. True. Shade the half plane containing the origin, which is above and left of this line. Step 3. Find the intersection of the two shadings. The feasible region is the area satisfying both inequalities simultaneously, the overlap of the two half planes. Visually, it is the wedge-shaped region between the two boundary lines on the side that contains the origin. Step 4. Find the corner point where the two boundary lines meet. Solve the system x plus y equals 4 and x minus y equals 2 using elimination by addition. 2x equals 6, so x equals 3. Back substitute 3 plus y equals 4, so y equals 1. The corner point is 3, 1. Step 5. Classify the region. The two boundary lines define an open wedge that extends to infinity to the lower left. Combined with the requirement that we be on the origin side of both lines, the feasible region is unbounded extending toward the lower left. The single corner 3, 1 is the only finite vertex of the region, so the feasible region is the wedge below x plus y equals 4 and above x minus y equals 2, with corner at 3, 1 unbounded extending to the lower left. The big lesson from this example is the half-plane intersection workflow. Graph each inequality, find the overlap, identify corners by solving the boundary systems. The corner finding step uses the Section 6 system, solving methods connecting the inequality work to the equation work. Here is the second worked example. Graph the system of three inequalities x greater than or equal to 0, y greater than or equal to 0, x plus y less than or equal to 6. Identify the feasible region and all corner points. The first two constraints restrict the solution to the first quadrant, and the third caps the sum at 6. Step 1. Graph each inequality. X greater than or equal to 0 is the right half plane bounded by the y-axis. Y greater than or equal to 0 is the upper half plane bounded by the x-axis. X plus y less than or equal to 6 has boundary line through 6, 0 and 0, 6, with the half plane below containing the origin. All three inequalities are non-strict, so all three boundaries are solid lines. Step 2. Find the intersection of the three half-planes. Inside the first quadrant from the first two constraints, capped by the line x plus y equals 6 from the third constraint, the feasible region is the triangular area with vertices at the origin 6, 0 and 0, 6. Step 3. Identify the corner points. The three corners are the intersections of pairs of boundary lines. X equals 0 and y equals 0 meet at the origin 0, 0. X equals 0 and x plus y equals 6 meet at 0, 6. Y equals 0 and x plus y equals 6 meet at 6, 0. Three corners total. Step 4. Verify each corner is on the correct side of every inequality. At 0, 0 x is 0, which satisfies x at least 0, y is 0, which satisfies y at least 0, x plus y equals 0, which is at most 6, all three satisfied. At 6, 0 similar checks all pass. At 0, 6 similar checks all pass. All three corners are valid vertices. Step 5. Classify the region. The feasible region is a closed triangle with three vertices, finite area, fully bounded. The bounded region is suitable for linear programming optimization, with finite optimal values at one of the three corners. So the feasible region is the triangle with vertices at the origin 6, 0 and 0, 6. The big lesson from this example is the bounded feasible region case with multiple corner points. The triangle structure is one of the simplest feasible regions in linear programming, and it appears constantly in introductory operations research as the canonical example. The corner point identification uses pairwise system solving exactly as in the previous example. 3 mistakes that catch every algebra student during their first weeks of System of Inequalities work. Each one is fixable with a small explicit habit applied on every problem. First mistake: shading the wrong half plane on one of the inequalities, producing an incorrect overlap region. A student plots the boundary line correctly but shades the half plane that does not satisfy the inequality, often by intuition rather than by the test point method. The fix is to always perform the test point step on every inequality, plugging a specific point like the origin into the inequality and shading toward truth as we covered in section 4 lesson 8. The test point removes any guesswork about which side is the correct half. Second mistake: using the wrong line type for the boundary with solid line for strict inequalities or dashed line for non-strict inequalities. The convention is solid for less than or equal to and greater than or equal to because the boundary points are part of the solution, dashed for strict less than and greater than because boundary points are excluded. The fix is to memorize the convention and apply it before drawing any line. Read the inequality symbol carefully and choose the line type accordingly. Third mistake: identifying only some of the corner points of the feasible region and missing others. With 3 boundary lines, there are 3 pairs of lines and therefore up to 3 corner points. With 4 boundary lines, up to 6 pairs and up to 6 potential corners. The fix is to systematically check every pair of boundary lines, find the intersection point, and verify whether that intersection is inside the feasible region. Some pair intersections fall outside the feasible region and are not corners, others are valid corners. The systematic check ensures no corner is missed. Systems of inequalities are the foundational tool of linear programming and constraint optimization across operations research, manufacturing, finance, and applied math. Anywhere multiple constraints must hold simultaneously and the goal is to find feasible operating points, a system of inequalities captures the constraints and the feasible region. 4 broad sectors below. In linear programming, the foundational technique of operations research, the feasible region is exactly the intersection of multiple half planes corresponding to linear constraints. The optimal solution to a linear programming problem with a linear objective function always occurs at one of the corner points of the feasible region by the fundamental theorem of linear programming. The corner finding skill we practice today is therefore directly the corner evaluation skill of linear programming, and the next lesson covers the optimization step. In manufacturing and operations management, production schedules are constrained by multiple resource limits: total time available, total raw material, total labor hours, equipment capacity, demand minimums and maximums. Each constraint is a linear inequality in the production quantities of the various products, and the feasible region in the production quantity space is the intersection of all the half planes. Production planners use linear programming on these systems to find the optimal product mix that maximizes profit or minimizes cost subject to all the constraints. In diet and nutrition planning, meal plans are constrained by multiple nutritional requirements, calorie limits, and budget caps. Each constraint becomes a linear inequality in the food quantity space, and the feasible region is the set of meal plans satisfying every requirement. Linear programming applied to such systems produces optimized diet plans for hospitals, athletes, and dietary intervention studies, all built on the system of inequalities mathematics from today. In game theory and strategic analysis, Strategy spaces of two-player games are often partitioned by pay-off inequalities into regions corresponding to different equilibrium outcomes or rational responses. The feasible region analysis identifies which combinations of strategy parameters lead to which game outcomes. Economists, political scientists, and AI researchers use this kind of strategic visualization to analyze games of conflict and cooperation across many applied scenarios. 3 things to take with you from this lesson today. Systems of linear inequalities are the foundational tool of constraint optimization across operations research, manufacturing, finance, and applied math. And the half-plane intersection technique we covered today applies to every standard problem in all of those fields, and in many more besides. First, a system of linear inequalities is a collection of two or more inequalities that must hold simultaneously together. Each inequality describes a half-plane on the coordinate plane, and the solution to the system is the intersection of all the half-planes, the set of points satisfying every inequality at once. The intersection is typically a polygonal region with straight line boundaries, called the feasible region of the system. Second, to solve a system of inequalities graphically, graph each inequality individually using the half-plane method from Section 4, Lesson 8, identify the intersection of all the shadings, and find the corner points by solving the boundary systems pairwise. Corner points are the intersections of pairs of boundary lines treated as equations, computed with the Section 6 system solving methods. Classify the feasible region as bounded or unbounded based on whether all the boundaries close the region into a finite polygon. Third, the corner points are foundational because in linear programming the optimum of any linear objective function over the feasible region always occurs at one of the corner points. The corner finding skill we practice today therefore feeds directly into the optimization work of linear programming in the next lesson, and the same idea generalizes to many variable systems through the simplex method in higher math classes. Each pair of boundary lines produces a candidate corner, and you should systematically check all the pairs in any system to find the complete vertex set. Some pairs intersect outside the feasible region and are not actual corners, but the systematic check ensures no real corner is missed. Coming up next, the lesson called linear programming, where we add an objective function to a system of inequalities and find the corner of the feasible region that optimizes the objective. Linear programming is one of the most widely used techniques in all of operations research, and it scales from 2 variable algebra problems we cover here to many variable industrial problems with thousands of constraints solved by computer software in production planning, logistics, transportation scheduling, financial portfolio optimization, and many other applied scenarios.